Welcome, everyone, and thank you very much to Bruno and the London Clojurians. I really appreciate the regular cadence of having an online meeting like this is fantastic for the community, and so I really appreciate London Clojurians and all the other meetups that have been doing online talks and putting those things out there. It really is important for the community and for us, representing to the broader developer community to have that venue, a venue like this, and the other ones. And so it's important. I'm glad you're doing it. Thank you, and I'm happy to be here. So this talk came out of originally some questions that came up at Nubank internally. We have just internal Clojure forums and people to ask questions. I said, oh well, I could do a little talk on that, and ended up breaking it into two parts. One that's talking mostly about reflection and type hinting, and then the other one that was more about numerics and boxing. And so this is a combination of those two talks. I'm gonna there is a lot of material in it. I'm gonna try not to be more than about an hour, and then I might break at the end of the first part and ask for questions then, and we'll break it again at the end to ask questions at the end. So I think that'll probably work well. Let me get to the right window. All right. So these are kind of the two parts. The first part, I'll do a very, very quick background on some Java things in case you're coming from Clojure but not as familiar with Java in the back end. I'll talk about Java interop in Clojure, about reflection, how to avoid it, and some common pitfalls. And then part two, we're really going to focus more on numerics and boxing. So we'll talk about how to get primitive function parameters, how to use let bindings to leverage primitives, and loop recur, same thing. And then a little bit about the overflow options and some of those things in math stuff, basically. I do have some examples throughout. We can ask about those at different parts. So part one, so Java object-oriented programming. I'm going to give you the 2 or 3 slide version of what you need to know about Java. So the general organization in Java is that there are modules which contain packages which contain classes. In general, we mostly ignore modules in the Clojure world, and maybe a lot of people in Java world ignore them as well. They were just added in Java 1.9, which was a while ago now, but that seems relatively new. They have not had a ton of uptake. In my opinion, they're kind of a bad idea, but that they exist. So classes have static fields, which are data, and methods, which are code. And classes can be constructed to create objects or instances of that class. Objects can have fields that are on a per object instance, again, data, and methods that you can invoke on one of those objects, which is, again, code. Really, all data in Java is stored in either static fields or in object fields, instance fields. So those are the two places we actually store data, really, in Java. There's 7 primitive Java types. These don't all exactly exist at the JVM level. Things like Boolean actually is not a JVM thing. It's kind of a fiction created by Java, and sort of the int char thing is also a little bit fuzzy down at the JVM level. But you don't really care about all that. These are the primitive types that exist in Java. Clojure is built on Java, so that's what's important to us. You can also have objects, object references. That object reference might be missing, and if it is, then it's null is the not here marker, and we call that nil in Clojure, but it's the identical thing. And then we have arrays, which are kind of a weird thing. They are references, but they are references of some other type, and they have some special fields and some special handling. I'm actually not going to talk about arrays a ton. We'll talk about it a little bit, but that's kind of a one major area that I have omitted from this talk mostly. So that's maybe a gap. I'll tell you up front. Primitives versus box types. This is kind of in some ways, the efficiency split, the trade-off matrix that was made by Java in the early days, and it has really caused a lot of decisions later on. And they're looking at possibly sort of bringing these things back together in Project Valhalla, which is a very active Java project. And the basic idea of Project Valhalla is to get the benefits of primitives, but the sort of invocation model of objects at the same time. So they kind of had this trade-off. Primitives use less memory. If you have a Java int, a primitive int, it takes 16 bits in memory. Whereas if you have a Java integer object, so the object form of it, then you've got some object overhead and some field overhead, and they generally take more space in memory. But objects can have code attached to them. So that's the sort of the trade-off, is you get this sort of object programming model with the boxed form of the primitive, and you get better memory and speed in the unboxed form. So in Java and in Clojure, since Java 1.5 in particular, a lot of the boxing and unboxing is just implicit. So you can have a Java method that returns a primitive int and return an integer object, and it will unbox it, or vice versa. You can return a primitive int and it will box it into an object for you. And Clojure does a lot of that for you as well. A lot of times you don't explicitly see boxing and unboxing, switching between this primitive and object form. So the other thing to say about this is that if you're going to do math, that you're going to add numbers, multiply them, or whatever, that's always going to happen on primitives effectively. So anytime you've got boxed versions of the objects and you want to do math, you're going to have to unbox them somewhere. Somebody is going to have to unbox them, do some math, and then possibly rebox them. If that sounds like extra work that takes time, then yes, it is. And so that's why we'll talk about numerics and boxing later on. Java interop in Clojure, there are several ways to do things, but these are the common ways to do things. So the main things that you're going to do with Java interop are construct a new object. But to do that, you say the name of a class with a dot at the end. You can invoke an instance method on an object by saying dot some method on some object with some args. You can invoke a static method by saying class/method. You can access a static field by just saying class/field. So you don't put that in parentheses, you just reference it. You can obtain an instance field, actually two common ways. .dash says I want to obtain the value of a field. If you use just .field, that you would see overlaps with the .method above. And in fact, if you only have a method or a field of that name, it will just figure out which one you mean. If you have both, then it's going to prefer the method one. So in that case, you have to use .dash field. And so that's the unambiguous case. Generally, if I'm going after a field, I will do that to make it unambiguous. It also is a little more portable to ClojureScript and things like that. And then a class, just with the class name, will give you back the class object that represents the class that you've named in the symbol. There are other things. This is an incomplete list, but that is the vast majority of the Java interop methods that you're going to use. So performance concerns. There are really two performance concerns that map into the two big parts of this talk: reflection and box math. So reflection has to do with slow invocation. We'll talk about that more. Box math has to do with all this boxing and unboxing mess. reflection lets us inspect class fields and methods at runtime. And so we can look at what's in memory. We can traverse through, the class's find methods, invoke those methods, find fields, get the values of fields, things like that. The big upside is it's dynamic. The big downside is it's slow. So it's generally 10 to 100 times slower than a compiled invoke. The speed of it really has changed over time. It used to be really, really slow. Now it's just merely slow. And in some, I think in Java 17-ish timeframe, like that's maybe the optimum. I think they've been working on re-implementing reflection using invoke dynamic and some other things like that. I don't think that's actually improved the speed of it much yet, but maybe it will. So eventually, maybe it won't matter as much, but right now it does. So Clojure will try to avoid Java reflection if it knows enough information to do that. But it will fall back to runtime reflection if the calls are ambiguous. In performance-sensitive code, this is going to matter a lot because obviously invoking something that's 10 to 100 times slower, especially if it's in a hot loop or your main transaction path or whatever, is slower. So we want to avoid that. In cases where you're not in the main path, it really doesn't matter. So it's important to stress about this, the appropriate amount in the appropriate place. So this is an example of a call that might use reflection. This is a upper method. There is an upper string method in Clojure.string, but if you were writing a method like this, it takes some value s and calls to uppercase on it. We as humans might infer that that's probably a Java string, but obviously the Clojure compiler doesn't know that. It doesn't know anything about what the type of s is. As far as we know, it's some random object. You can make a reflective call to invoke to uppercase on some arbitrary object s. That's totally fine. At runtime, we actually know what kind of thing s is. We know that it's a string, and we know what method string has. So we can figure that out at runtime, and that's what Clojure will do if you haven't told it enough information. So I think this says exactly what I just said, pretty much. One of the big downsides, this last bullet, is that if you're using reflection, then it's much harder to inline that invocation because you've turned what was one call into a whole bunch of calls to do all this work at the top. And that makes your method body much larger. It makes it harder to inline. And inlining is really the path to most JVM optimizations. You're trying to get bigger chunks of code that you can optimize at the same time based on its runtime profile. You want to compile this big chunk of code into, a smaller chunk of assembly code and take advantage of constraints and things that you see in that bigger chunk of code. So so it has a lot of follow-on effects. If you want to find out when this is happening, you can do that with the warn-on reflection dynamic binding. I recommend that in any namespace where you're doing Java interop, immediately after the namespace operation that you call set warn-on reflect to, or warn-on reflection. Now I'm second guessing myself. I have both of them. One of those is right. So I think it's warn-on reflection, but whatever that is, you should set it. You can also set it globally during compilation. Like depending on your tool, you can do that different ways. If you do that, that's fine too, but you may be doing it more broadly than you need. You may also be checking it on some of your tooling, other libraries, things like that, maybe places that you can't actually make the changes to get rid of that reflection. So that may be too much. So just as an example here, if we're in some namespace, so this is how you would set this in a real namespace. Right after your namespace call, you set warn-on reflection true. And then you're going to have this Clojure function that calls some Java method. And then when this is compiled, which might be at load time, if you're loading a source file, you're going to see reflection warning with reference to field to uppercase can't be resolved. So it doesn't know if it's a field or a method. So it could be either. And so it doesn't know what S is. So it doesn't know what that is. So how to stop reflecting? And the big answer is to basically provide enough type information that Clojure can, at compile time, find the target method you're trying to compile, you're trying to invoke. And so the target class is probably the most important part of that, but you also need to specify enough to resolve any overloaded methods. And the arity is implicit in the call, so we're always using that information to try to find the correct method in the class. So type hints are basically metadata that tells Clojure, the Clojure compiler, that an object is some type. They really are hints in general, and we'll see some exceptions to that later. But even if they're wrong, the code may actually still work reflectively because there is still an object path that exists. Sort of the reflective object path still exists there. The syntax for type hints is generally to apply metadata with a valid type hint in front of the expression. So it gets applied to that expression. Valid type hints can be several different things. They might be a fully qualified class name or a short class name that is resolved on import. That's kind of the most common thing you'll see. There are also a bunch of special type hints that the Clojure compiler understands. There's one for each of the primitive types, so byte, short, long, float, double, char, boolean. There are also ones for arrays of either objects or other primitive types. Those are the pluralized form of all those, plus objects is for an object array. Void is actually a valid return type hint. There are very, very few places where that's needed, but it does exist. I think maybe in like protocol methods when you're implementing a Java interface, there may be some cases where it's useful to do that, but very rarely. And then you could also use strings that are internal Java class names. So things like Java util date is a valid class name. So that's another example. Where to put them? So the main places you put these will be either on function signatures, either on the parameters or before the parameter vector to type hint the return type, or in let forms or macros derived from let, which is most things that have sort of a let style binding. A lot of those are macros that expand to lets. So generally anything like that probably is a good place to do it. You can put them on method invocation arguments. So directly at the place where you make a Java method call, you can type hint the argument. You may be able to type in the argument. So one caveat with that is that that and also in let forms is that you can't type hint things that don't take metadata. So all Clojure collections take metadata. That covers a lot of things. Things that have been let bound into a local symbol can have metadata, but things like numbers cannot, or Java strings cannot, because those things are Java things, and we can't modify. We can't add metadata to those types because they're closed types, basically. But you can always pull that value out into a let bound symbol, and then you can type in at that point. Another place you can put metadata is on def vars. I'm going to talk more about that in a minute. Places you should not put type hints are on defin vars. So when you're declaring a defin, generally you should not put type hints on the defin var itself. You should put them on the parameter return types. There are a couple of reasons for that. I'm not going to go into a lot of detail about that. We can talk about it if there's questions. Should you type in Clojure data types, things like persistent hash map or persistent array map or iPersistent map or things like that? Generally, no, or keywords, stuff like that. The core lib is designed generally to not need type hints for concrete Clojure data structures. So generally, you should not do that. There may be some very, very specialized cases where that's useful, but in general, I would assume don't do that. You should really focus on Java interop calls. That's the place where these really make a difference, because that's where we're selecting the Java method to call. Let's see, hinting our example. So we go back to our example here, the upper method. It is sufficient to put a type hint just on the argument s that's being passed to the toUpperCase method. So the question is this the best place to put it? This place is totally fine. That's not a bad place to put it. Another place you might put it is on the function parameter itself. It has a couple of possible benefits there. The first is that it actually gets into the signature and then you can see it from outside the function. That might be useful as sort of documentation. It also would allow you to make multiple calls with that parameter s inside the body of upper. So we're only making one call now, but if you're making more than one, generally specifying it earlier allows you to reuse that type in information in multiple places. So that could be useful. So I here would probably put it on the function parameter. The other case is also fine. You generally want to place as few type hints as possible. The Clojure compiler will track the return type of Java method calls. Once it understands which one you're trying to call, it knows what the return type of that is and can then use that as type inference for subsequent calls. So in general, just moving type hints earlier in the method will allow you to get maximum benefit from that. And the goal is to really remove ambiguity in all the Java function calls that you're making in the method. So this is an example of some code I pulled out of somewhere. The Java method call here is .submit. It is being called on an executor service, and the task here is a Java runnable or callable. And so we want to focus here on making sure that this, if we want to remove reflection, we have to focus on the Java calls. There's only one here. So both executor and task need to be unambiguous at the point where you do reflection. So you could type hint in the submit call, but from the advice that I've already given, I think it's better to actually put it on the function argument. And so I've added that. I've also added a return type hint of future. That means that if somebody calls submit task somewhere, it will, the Clojure compiler will be able to leverage the return type hint of this Clojure function call. So that's potentially useful for callers of this method. It also serves as documentation that could be useful to you. And then task is actually, I believe there's submit methods for both runnable and callable. And Clojure functions are very cool in that they are both runnable and callable. But the downside is that means that it's ambiguous which one you're trying to pass to submit here. So you need to type in it to one or the other. You could type in it again directly in the submit call where it says task on the last line, or you can type in it inside the let. Either will work here. Type in the let would allow you to use task and pass that to multiple calls. Generally, I prefer to do it earlier, but either is fine. So here's another snippet of code. It's got a bunch of stuff in it, but it's not really important to understand all the details of this. I just want to focus your way you should think about it. So when I look at this, I see several Java method calls. I see .toPath. So that's calling something on file, which means I need to know what file is. So you need to type hint that to something. And you could choose to do that in the call or on the function parameter. So I'm going to prefer that one, the function parameter. I see files is directory, which takes a path and an array of link options. So you're going to need to do something with that. I see a files new directory stream. So that operates on path. So I've now seen two places that that say that we need to know what path is going to be. And then the .to file inside the map v at the end. So there's 4 method calls in here, Java method calls. And so you need to think about each one and ensure that the types are being specified for all these. So file, yeah, let's go for it. So by type hitting file at the top, we know that any place the file is used inside the body we're going to know what the type of it is there. So that covers the first call to toPath. Now, Clojure, the Clojure compiler knows that toPath, once we know that it's a file, will return a path. And so you can assume that the type of path in the files is directory and in the files new directory stream, that both of those calls know what path is. Into array is something that is effectively a constructor function for a typed array. And so Clojure understands that. So you don't need to put a special type in here in that case. You've explicitly made a typed array, and Clojure will use that. So we don't need to actually put any type ints on the files is directory or on the files new directory stream. Inside the map v, this is an anonymous function. So an anonymous function has an argument, but we've lost any sort of notion of what the type of that is. And so we're going to need to add a type hint there to sort of recover the type of the thing that is inside entries. So that inference is not flowing through here. So I added 2 type hints, and that should be sufficient to fully work through all the type hints in this, all the reflective possibilities inside this method. If you're using the warn on reflection, you can you can double check that by trying to compile that and finding it. And you might want to just do one at a time. Add the top one, run it again, see what which calls are still reflective, and so forth. A common question I see is how do I do Java generics in a type signature? And the answer is you don't care. So generics are actually a part of Java, but not part of the JVM. So the JVM does erasure, and it erases, the Java, I guess, does erasure and erases those generics in the bytecode. So because Clojure is meeting the JVM at the bytecode and Java at the bytecode, it's going to just be dealing with the raw types, no generics. So if you have, for example, a Java method that takes a list of string, just list is sufficient, a sufficient type in Clojure code for that. And another common area that we see problems is with invoking Variadic Java methods. So you might see a method like this third bullet down here, public static t list of t as list t a. So if we unpack what that all means a little bit, the method is called asList. It's taking a 0 or more t's and returning a list of t. And then t is defined at the front as a generic template parameter. So it's just basically saying it's taking a bunch of t's and returning a list of those. So that's going to get erased in the JVM to being just something that returns a list and takes an array of objects. So the Variadic Java methods are implemented in the JVM as an array of type t, but T is a generic type. Generics get erased. So in this case, it'll get erased all the way back to object. So asList is really a Java method that takes an object array. That it's unfortunate that you have to know all of that. And so this is something that we've been working on a bit. We were hoping to have some solution to this in Java 1.12, but we still have some lingering questions. And I think we're going to push that out of 1.12 and have it at the front of the queue for the next release to look at. But we have done a lot of good work on it, and I think come up with some options to think about there. Is there anything here I haven't said? You might find, so saying, so there are existing type hints for things like arrays of primitives or an array of objects. So the objects type hint is sufficient in this case to type in it. But you can also use the Java internal type name for an array of objects, which looks like this line at the bottom, which is the open brace there indicates an array, and then the L java.lang.object semicolon is the Java internal name for an array type, for an object type. So you can actually use that as a type hint, which is not obvious to anyone. So don't feel bad if that's confusing. So this is, again, saying most of that same stuff. You can use the primitive array types, but strings as type hints, but really you should probably just use the simplified Clojure versions. That's why they exist. So you don't have to know all that. Def and var meta, I mentioned before that you should not put return type meta on vars. This is kind of the reason why. For historical reasons, the metadata that you have on a var is evaluated, whereas the metadata that's inside a function definition is not. That's passed to a special form that gets handled. So if you try to put a type hint on the var average, the var name average, that long is actually, the symbol long is going to get evaluated to the clojure.core/long coercion function. That is not a valid type hint, and that's not what you intended. So that's not going to work. It is possible to type hint the var if you are careful about how you do that, either by using a explicit metadata map with tag, or by quoting it appropriately and doing those kinds of things. But really, you should not do that. You should really type in the parameters, the vector parameters of the function itself. So that is, I'm going to say, the right way to do this. So that's my recommendation. Generally, you should probably just use def less. So that's the big the big advice is use less global state in the first place. But if you do have global state and you really want to mark it with a type hint, it is possible to do that. Because it has the same issue as the same var metadata issue as defen. One way to do that is what's shown here. You can use tag and then a quoted double, and that will give you the right thing. So this here creates a var e that has the value from math e, but it's probably better to just use the value that's in math e, or to use the value that's in clojure.math, the new namespace that has an e constant that does this correctly for you. Those are better options. We get some questions about const metadata a lot too. There's a lot of confusion about what it does and how it works. In general, most people use it wrong. So that's and it would be fine in most cases to not use it at all. So that's the first pass advice is don't use const. But the second pass advice is if you really want to use const, what it does is when the Clojure compiler compiles a reference to a var that is marked as const, it takes the value of that var and inlines it directly into the code that's using it. And so it really should truly be a constant. It can't be a thing that needs to be evaluated, because it's not going to be evaluated. It should be ideally something like a number, a Java string. It can actually be Clojure data that is constant data that will be constructed once and then used as a constant. But it's really easy to do something in here because we're used to defing Vars and being able to evaluate things in the initial value slot, where math E is here. It's easy to get the wrong impression there that you can do that with const vars, and you can't. So it's not going to do what you want in that case. And then at runtime, because it's inline directly into the call site, it does not have to dereference the var. That's the big benefit you get. Most of the time, that will make no difference to you whatsoever. So that's probably not your performance issue. But if you are making a literal numeric or string constant, something like that, you can do that via this. You don't typically need to actually tag it with the right metadata type. That usually is not going to matter for you, but you can do that and mark it as constant if you want. So summary from the reflection stuff. You want to avoid reflection on Java method calls that are in hot paths. You want to find cases of reflection with warning reflection and fix that by specifying type hints. You should make those as minimal as possible, generally moving them towards the front of the Clojure function will allow you to get the biggest benefit from that and save the fewest amount of type hints, and then rely on type reference to carry that type information through the rest of the Clojure function. So that is the end of part. All right, well, I'm going to move on to part 2 then. So numerics and boxing. So the parts of this that I want to talk about are primitive function parameters, let bindings, loop recur, and math. So primitive function parameters. I've said before that all Clojure functions take and return objects. Type hints in general don't change that. So in that previous example we had that took an S and we type hinted it as a string, the compiled code does not take a string at that point. It still takes object. So in general, type hints don't affect the parameters of compiled Clojure functions, except for one special case, and that is, well, I'll move on to that in a second. So let me give you an example of that. So here, this average function takes A and B, and it's averaging those with some math. So what I just said was Clojure functions always take objects and return objects. So the types of A and B are object, and the return type is object. And so if you decompile this, so this is actually if you take that code, compile it to bytecode, and then decompile it back to Java. So this is sort of the Java translation, which is not exactly the right thing, and I have omitted some details. So this is a bit of a pseudo code rendering of it, but effectively what you get is this. So the average function gets compiled into a class. That class will extend a function, which is a base class, sort of a helper base class used by the Java implementation of Clojure that implements the ifun interface. So you don't see ifun here because it's up in the base class. And it's going to get compiled into 2 different Java methods. Taking the bottom one first, this invoke is the implementation of ifun. It takes objects always and returns object always. And then it's going to call invoke static. So invoke static also takes objects A and B, and then has the translation of the body of the method. And anything to do with numbers generally will, in Clojure, will compile the calls back into the numbers class, which is part of the Clojure implementation. That's clojure.lang.numbers. And numbers provides polymorphic implementations of all of the mathematical operations that you use in Clojure. So it has an add method that can take different combinations of types, in this case, objects A and B, and it knows how to then figure out what kinds of things they are, widen things if appropriate, add them together and return a number. Because these are object inputs, it's going to return an object output. And then that's going to be called, then we're going to call divide on the result of that, and a 2, which is a primitive long. So this number here does get actually converted into a primitive object, a primitive value, not an object. And then it returns the result of that, which again is an object. So we can tell there's boxed math happening here because anytime there's objects involved, that's boxed math. So something is going to have to take those objects, unpackage them back into primitives, and then do the math, and then maybe package them back into objects. So how can we change this? There are 2 special type hints in Clojure, which are long and double. And those primitive type hints for functions with no more than 4 arguments will create a special primitive invocation path. And that path will be used whenever you can detect at the call site for that function that we have primitives that can be used. The path is never used when you're invoking the function as a higher order function. So it's very important that if you make a function that has a primitive invocation path, and then you map it over a collection of, integers or something like that, we're always going to be using the object path, which still exists. So you're adding an additional primitive invocation path, but you don't actually get the use of that in higher order contexts. That may not always be the case. So this is an area that we continue to talk about off and on, and would love to have an alternate path there to maybe make use of that. It's complicated, so we'll see. So here's an example of a variant of that method we just had. And the only thing I've done to it is add double type hints on A and B, the parameters, and on the return type. And I also, the other thing I did was I changed the primitive long 2 to a double 2.0. And that's because I know that then we don't have to do any widening or narrowing conversions. And you can see that when this compiles, let's look at the body first. The first body here in invoke static is just A plus, this is just because I've gone through decompiling here, A plus var2, and then divided it by 2.0. So this is all just base Java primitive math, which is what you want to see here. It's not doing any boxing or unboxing. There's nothing special here. You're getting the identical implementation you'd get if you wrote it in Java, basically. So if we go back up to the top line, you'll see that it says what it did before, except that it also implements ifun.ddd. So ifun.ddd is another interface. It's defined nested inside the ifun interface, but it's another interface, and its signature is the method that's down here at the bottom of the class, invoke prim. So invoke prim, you'll see, does not take objects. It takes doubles and returns a double. And why is it called DDD? It's because it has a double return type. That's the first D. And it takes 2 doubles. That's the second and third D. So because we support this for up to 4 arguments, you've got 5 letters there. They can all be D for double, L for long, or O for object, which is the default. And so there are 5 factorial different variants of these interfaces that allow you to invoke the primitive through a specific path. So if you go out and look at the ifun interface inside the Clojure implementation, that's what you'll see, which means there is an ifun.lol. So that's always fun. People like to joke about that. We can also then, some other things to notice here is that invoke prim calls invoke static, which now doesn't take objects. It now takes doubles. I guess I didn't mention why there's an invoke static. So to take a little digression on that, you may have heard of direct linking as an option when you compile Clojure code. And what direct linking does is it says, when I try to invoke a function, it's like here, it'd be the average2 function. If I try to invoke that function from somewhere, at compile time, if I have direct linking turned on, I will not look up the var numerics average2 and then find its function object and then construct it and invoke it with the invoke method. Instead, I will just call directly to the invoke static method. And so it removes a bunch of overhead in the call site, basically. That's good because there's less code run. It's good because you don't have to go through the var lookup, which is a synchronization point. It's good because there's less code, so you can do inlining easier and in larger chunks. So it has all kinds of benefits. And you lose, the big trade-off here is you lose the dynamicity. The code that's compiled with direct linking no longer uses the var. So it's not, if you change the var, you're not seeing the benefit of those changes. And so that's the trade-off. If you are compiling code to run at production time, and you're not planning to change the value of this function var, which most people don't most of the time, then you can give up that dynamicity and instead get a bunch of performance out of it. So that's why direct linking exists. And Clojure Core is direct linked by as built right now. And then you can use that yourself if you want to do that. So that's why there's invoke static. Invoke is the normal ifun interface, and invoke is what you'll get called in higher order contexts. And so if you're mapping this average2 over two streams of numbers, for example, then you're going to call through invoke. And you notice that invoke, also drives back to invoke static, but it's got to do all this unboxing junk. So the things it's going to assume that you're doing numeric stuff because you're driving towards long or double inputs. So it's going to do that cast. It then has to cast that into a double primitive that can then be invoked. And if it's not a double, if it's something else, then these casts are going to fail at runtime. So that's kind of how the compilation works with primitive type ins. So where do you get primitives from to actually invoke these things with? That's the next question. So let will create local bindings in some lexical context, some lexical scope. Those local bindings, the Clojure compiler understands that they might have primitive numeric values. So they don't have to just be objects. They can also be literal primitive longs and doubles, or in any of the primitive types. You can get those values from either using literal longs and doubles. So just like putting a number in the code there, that's fine. You can invoke a Java method or a Clojure method that's marked as having a primitive return. It will retain that primitive value. You can invoke a coercion function, like there's a coercion function with the name of the type for all the different primitive types. So there's an int, long, double, float, all those things. And Clojure will respect that and understand that you're getting back a primitive type. So let will not, at the point where we use those values, if they are primitive values, we'll make use of those directly without boxing them and unboxing them or whatever. So generally, you're going to want to use let bindings to make things into the right primitive types and then make Java interop calls or Clojure interop calls or Clojure function calls or whatever you need to do. So this is an example of some code. So this is the Clojure code at the top and the Java decompiled version at the bottom. And here, this let bindings function is going to return a primitive long. We're going to let rads or radians be math pi. So math pi is a Java static field that's of type primitive double. So we know that that rads is going to be a primitive double. That primitive double is passed to math 2 degrees, which is a static function static method in Clojure, in Java, sorry, too many contexts. So it's a Java method that takes a double and returns a double. So we know that degrees is then a primitive double. Angle is a constant. So here it's a primitive double. And then we can add together degrees and angle. That's all going to be presumably primitive math. We're using a coercion function to ensure that we get back a long instead of a double here. So if you look at the compiled version of this code, it's all primitive calls that are being done here. The calls to the Java static field, Java static method are all, there's no boxing or unboxing there. The RT longcast is actually going to call, it's going to end up calling, I think something in the math. I can't remember now if it does a primitive, I can't remember exactly what it does, but it's effectively casting a primitive double to a primitive long. And there's actually bytecode support for that call. So if you actually dive down to the bytecode, you'll see it's making use of the, I can't remember what the instruction is. It's probably D2L or something like that. So it's actually using bytecode to do that ultimately. And then it returns that long value. So there's no boxing here, no unboxing. This is basically the same efficient code that you would write in Java. And then there's some invoke and invoke prem paths there, which we've already talked about. Loop recur. So a lot of times when you're doing anything algorithmic, you're going to need to loop and recur over things because you've got any kind of higher order function use typically takes you out of primitive land and back into object land. And generally, you're not going to want to use map or something like that, or reduce to operate on things that you want to stay primitive. So that means instead, you're probably going to end up writing a lot of loop recurs. Recur will retain primitive longs and doubles through the recursion. So that's really important that recur here is going to take a long value and rebind a, which is a primitive, back to a new primitive value. And there's no boxing or unboxing that happens across that. Occasionally, it would be really useful to have this for int as well. And that's something that there is a ticket out there. And that's something that's probably pending a discussion still about whether that would be a good thing to do. The main place that comes up is in Java, where int is used as the index type for arrays and Java collections and strings and all those kinds of things. So a lot of times it comes up as a thing that would be useful to have. I'm not sure in today's modern Java if that's all just completely irrelevant. It has in the past been a source of small performance differences between Clojure and Java, but maybe a future enhancement. So the compiled version of this code here, you'll see it initializes a to a long, a primitive long. It does a primitive long comparison. It calls numbers.inc, which actually is calling into math.incrementExact, which is going to increment it by 1, but it also does an overflow check. So there is still an overflow check here, and that could be removed if you use something. Well, we're going to talk about unchecked calls in a minute. So that's a place where you could get a difference here if you wanted to. So that's loop and recur. One useful thing to know is that loop and let are actually the identical compiler expression. Recur is just sort of a special case that can happen in there. So all of the things that I said about let bindings are equally true of loop bindings because they're actually the identical thing in the Clojure compiler. All right, so math. So when we do math, we have to think about the possibility of overflow for fixed precision types. So fixed precision types only have so many bits to represent numbers, which means that there are some numbers you can't represent, and you need to do something if you encounter one of those. So the three big choices here are you can check, is it going to overflow? And if so, throw. That's sort of the default in Java. It's also the default in Clojure. You can check and instead promote your fixed precision type up to some arbitrary precision type that can actually do the operation that you've requested. And there's a way to do that in Clojure as well. And then unchecked is don't check at all and just allow the overflow to happen, which means you're going to take your fixed precision type, you're going to overflow and get some new value in the fixed precision type, but it may overflow from positive to negative or vice versa. So this is faster because you're not checking anything, but also possibly unsafe. So you do need to think carefully about when you use that tool. It is a thing that, and it's also something that you want to happen sometimes. If you're doing a hash calculation or cryptographic operations, there might be times when you actually want the overflow to happen mathematically. So that's another possibility for that. So the way that we say these things in Clojure, if just normal math operations in Clojure are use plus, minus, times, what those kinds of things will by default be checked math. And so if you try to, for example, add 1 to the long max value, you will overflow and get an exception at that point. If you want to check and promote to an arbitrary precision type, you can get that in Clojure by appending a quote. There's a complementary set of operations, all which have a quote added to the end. So plus quote is a function that does promotion for you. And then you can skip the check and overflow by using, again, a set of complementary operations that all have the prefix unchecked. So you can use unchecked add to add 1 here, and it will overflow back into negative. So that's another option available for you. If you want, by default, Clojure numbers are always longs or doubles, but if you actually want overflow semantics for integers, you can get that as well for using, that's again another set of operations that have int added to the end. So there's unchecked add int, and I think there's an unchecked multiply int, and all those variants. That again is particularly useful if you're doing certain kinds of like hash calculations or something like that. So so you can change the default overflow behavior from check and throw to unchecked by setting unchecked math to true. And this basically means that when that dynamic variable is bound to true, all of the invocations of plus, minus, times, etc., instead use unchecked add, unchecked minus, unchecked multiply, etc. This is a coarse approach to changing numerics. It's not visible at the point where you make the call. It's only visible from the scope of the dynamic variable. So it's easy to shoot yourself in the foot doing this. So I would generally recommend not using unchecked math in this way, and instead using the explicit unchecked functions in places where you know that that's an okay thing to do. So that would be my recommendation. You might also want to get warnings about when boxed math is happening. And so you can actually do that right now by setting unchecked math to the logically true value, the keyword warn on boxed. And so if we went back to this slide, this says true here. True is a logically true value. If you set that to warn on boxed, that's a logically true value. You will still get the unchecked math operations. But in addition, you will also get warnings for some, but not all cases where boxed math is happening. So generally, it's a little bit of a dangerous thing to use here because it has both an effect and a set of warnings. This is something that might be an area where we could do better in the future for that. It was sort of expedient for, I'm using unchecked math, and also I want you to warn me if I don't get that somewhere. It does have false negatives. So I want to have false positives. If you get a warning, it really is happening. But there are some cases where you don't see warnings, but boxing is happening. And one in particular case that I know of is if you have boxing that happens in a return path of a Clojure function, that's a place where sometimes that boxing happens implicitly through Java. And so we don't actually have a hook there to easily detect that. So you might miss some cases like that. In reality, I'd say the easiest way to make sure that you're not using box math is to use a decompiler or a bytecode inspector of some kind to look at the generated code and make sure of that. So this is an example of using warn unboxed, and the warnings you'll get if you have an add function that adds two numbers. Here we've got plus, and it's going to you'll get at compile time or load time whenever this function is compiled. You're going to get an unchecked. You're going to see that there's a call to unchecked add that takes two objects. So you're getting the unchecked behavior by having a true value for unchecked math, and you're getting objects here that are being passed in. So you can see the types of those. And it's pretty common when you're using warn unboxed to have most of your things being primitive, but occasionally an object leaks through. And so you'll see something like object in long here. That's usually a good hint as, oh, this first parameter somehow is an object when it shouldn't be. I want to talk a little about Clojure Math. So Clojure 111 added a new Clojure Math namespace. This is mostly a wrapper for Java Lang Math, but it narrows to only the long or double overload. Most of the methods in math are supported for either int or long or float or double, or occasionally more than that. And so the Clojure Math namespace narrows that to just the long or double overload, which are kind of the two main primitive types in Clojure. It will coerce inputs if needed, which becomes basically a no-op if it's not needed, and inlines that call to the place where it's being used. So you're going to get your ideal invocation of Java Lang Math in most cases. You can get a lot of the effects of that yourself by properly making the Java Lang Math call, but in general, it's going to be safer to call through Clojure Math. I would really recommend that. And then in addition to Clojure Math, I'll include the absolute value function, which is actually in Clojure core. And the reason for that is that it supports all of the numeric types, and it goes through the full polymorphic invocation chain that we use for all the other math operations. So that's why we put it in core instead of in math. That's generally better. And all of these are generally much, much faster than using the math numeric tower library, which has been around for a long time. It kind of simulates some of the sort of Lisp scheme numeric tower stuff, but that is backed by multi-methods and does lots of things that are slow. So it's more generic in some ways, but it's also generally slow. So I really would not recommend using that library at this point. And then this is an example of my hope for this talk is that you have a better model of what's happening under the hood, and you can look at a piece of code, and you don't need to run a decompiler or something like that to tell. You should be able to just look at some code and see what's primitive here, what's object, what am I likely going to need to do to get good numeric performance out of this. And I see this all the time. People, go into Advent of Code or whatever, and they're like, my thing is 100 times slower than it should be than when I ran it in C or whatever. And I don't need to look at the code to tell you that the problem is boxing. It's always either boxing or reflection or both. And so this is a function you might see of finding the distance between 2 points. When I look at this, I see no type ints. So I'm going to immediately assume that everything here is probably mostly using box math. You're also not getting primitives on the inputs or outputs because the points are packed into vectors here or some kind of indexed sequential data structure, presumably vectors, and then being destructured. So I know it's going to be faster to pull that apart. And I made a choice in the next slide about how to do that. There are multiple choices about how to do that. This is using Java Lang Math calls directly. Again, I would recommend using Clojure Math. And so you might I would immediately rewrite this to look something like this at the bottom here. I want to enable primitive functions to be passed in here. There are other choices you can make about how you represent a point in this case. You could use an array of doubles that allows you to pass primitives. You could use like a def type with primitive fields or something like that. There are some other options. The key is you really want them to be primitive doubles. So here I've passed them in as individual XY values and type in the return type. I switched the two that was a literal long into a literal double so that we're all working all in doubles. I've used Clojure.math square root and POW instead of using the Java ones directly. And then I can look at this and think from the inside out, these are doubles, the minus is a double, POW is going to get two doubles, it's going to return a double, and it's going to add those doubles and get another double and pass it to square root, which is going to return a double, which is going to turn out of the function as a double. So like without a lot of thinking, you can look at this combined with the mental model that we have now about how primitives flow through things and guess that this is probably a much faster function. And if you look at the decompiled version of this, this is what you'll see. The names are a little weird because of the decompiler path, but you can see that it's basically making the exact same implementation that you would have seen in Java. So I'm going to guess that's probably decent. Yes, there are other ways you can do some of these things like math.pow. You could do a shift to the right for those things. And there are other levels of this game. I'm not trying to get to all the levels. I'm just trying to show you the first pass. So helpful tools that you can use for this. Your brain is the number one tool. So I'm hoping that we will, that you will have a little better model about the insides here, the choices you can make about how you write your Clojure code. And then you can use that to think through what I expect to happen. If you want to do timing type things, there is a really basic tool built into your Clojure REPL everywhere you have it, which is to use time to do timings, do times to do repetitions. Here I find it often useful to do a double loop like this. I've written this code probably 10,000 times in my REPL. Basically, I want to do some code, wrap it into 1,000 repetitions, time that, and then wrap that into 10 bigger repetitions. And that allows me to get 10 sets of times. Generally, the first 2 or 3 are really slow because the JIT's warming up or whatever. You just throw those away and look at sort of where the times start to stabilize. You can get a good idea of, and you might need to adjust the 10 and the 1,000 here to get the right number. But this is a really dumb tool, but it's super effective. And so we've done a ton of work like that. If you want to move up to the next level of fancy, you can use something like Criterion. It does some of the same kinds of stuff in a more principled way and gives you much more stats and information. That's a good tool. I use it as well. Clojure Goes Fast has 2 great tools, has other great tools, but the 2 that I use the most are the CLJ Java decompiler, which you can use right at the REPL, or the async profiler, which gives you flame graphs. Both are extremely useful. I use them regularly. I use YourKit. I use IntelliJ's decompiler, and there's another plugin for bytecode viewing on IntelliJ that I use a lot. I don't know what exists in all the other tools, but those are some of the ones that I use all the time. And it's definitely worth using a decompiler or a bytecode inspector to verify that what you think you're doing is what you're actually doing. So that's always a good check at the end. So sort of a summary of the numeric stuff. Use typeints for long and double function parameters in return. Use let to bind primitive locals using either constants, coercions, return values, type inference, all that stuff. Recur only on primitive longs or doubles. Choose your overflow strategy carefully. I would recommend if you're using unchecked math, to use the unchecked operations so that you know what you're getting out of that. Use type hints to avoid reflection in Java interrupt calls. This is kind of harkening back to some of the stuff in the first half. And for performance sensitive code, use a decompiler to check what you got. And just some preview of coming attractions. Two things that are adjacent to the stuff in this talk that are probably coming in 112. We're trying to finish them up. Is functional interface adapters. So one of the big interop things that has gained some prominence in the last few years is being able to use Java functional interfaces. So there are a set of standard functional interfaces in Java util function. You can also mark arbitrary single method interfaces with the functional interface annotation. And you can even in some cases use arbitrary interfaces that happen to have a single method as functions. So it's really representing the invocation of a function as a typed interface in Java. So one sort of issue with that from Clojure is that Clojure functions are typed as ifun, and ifun is not a single method interface. It has all the different arity overloads in it. So you've got a square peg and a round hole kind of thing. So it is useful to be able to sort of adapt a Clojure function into a Java functional interface and pass that into a Java method that takes that functional interface. And so that is support that I've been working on. We're basically replicating some of what Java does using Evoke Dynamic to make those adapters. That is working great. We're still trying to decide exactly where and when those adapters get introduced. There's a lot of trade-offs there. So that's the part I'm working on right now. With method thunks, it's kind of the inverse problem. If I happen to have a Java method, in Java, you can now pass a Java method directly to something that takes a functional interface. And so it would be awfully nice if we could take a Java method and use it as a Clojure function. So it's kind of the opposite direction of adapter. And right now, typically you wrap that up in a anonymous function or something like that, but you have to apply type hints correctly. And do you do arity overloads? Usually not, but all that kind of stuff. So Focus has been working on making that stuff work, and we're hopeful that will also we'll get all the questions figured out on that. And in 112, you'll be able to take basically a Java method, so you might say class/method, and use that and map that over a collection, for example, without needing to create an intermediate Java Clojure function. So those are kind of the two big things that are kind of adjacent to this that we're working on, might be useful. And I think that is it. So I'm happy to take any questions.